Okay, moving on in our vapor tutorial, the next renderer in our list is the flow renderer. The flow renderer is kind of divided into two separate sets of functionality. The flow renderer can render streamlines and pathlines. The difference between a streamline and a pathline is that a streamline is time invariant. So when you plot a streamline at a single time step, you're mapping the trajectory of a particle that is independent of time. You're looking at the vector field of your simulation. So you're looking at your, for example, um, x, y, and z components of wind, usually u, v, and w, and you're just tracing the path along which a particle would follow at one single time step. That's a streamline. A path line does take time into account. So if you are in a hurricane and you took a pillowcase full of feathers and you threw it into the eye wall, a path line would show you where each one of those feathers would fly through the hurricane. So you're looking at the trajectory of a particle as it advects throughout time. So this video is going to be covering streamlines. The next one will be path lines. So with that, I will start Vapor. And again, I'm running Vapor from my command line over here since I'm running a development version, but most users after installing will open Vapor through the desktop icon or the icon wherever they have installed Vapor. So there we go, I've launched Vapor. And this data set is different than the hurricane data I've been using in the previous renderer tutorials. This is a tornado simulation that has been given to us by one of our super users, Lee Orff at University of Wisconsin-Madison, and he's generously provided us with test data to develop our flow renderer. He's also on our steering committee, so he helps guide our requirements, and he helps us make sure that we're implementing the right things to help scientists study their data. His data is a format, it's NetCDF, CF compliant, and it comes from a model called CM1, which is developed here at NCAR by George Bryan. CM1 is similar to WRF, but I think, as I understand it, it has a much higher resolution in the vertical dimension, and I think there's also some different physics going on. But anyways, I will import Lee's data as NetCDF CF compliant data. Navigate to my data directory, and I'm going to import these files. Now, I'm directly importing these files. This is not VDC like I've used in the past, so I'm not going to have my fidelity controller. The first thing I'm going to do, I usually start by throwing an image renderer to give an orientation and a context to where we're at, but this data is not geo-referenced, so an image renderer doesn't make any sense. It's just going to throw a world map on the bottom, and we're really looking at a 300 by 300 by 400 meter idealized domain without georeferencing. It's just a tornado. There's no landmass or anything. So to give us context, whoops, that might have been too fast. I just double-clicked on the slice renderer. I'm going to create a slice renderer and just throw it at the bottom of the domain so we can see the base of the tornado. So the first thing I guess I'll do is I'll turn it on. I'm going to pick a variable THRHOPERT, and what I understand, this is a potential temperature perturbation. So I'll select that one, rotate my scene, turn on my region mode, and I can throw this to the very bottom. And here we see the base of our tornado. Here's the cold pool, and here's the gosh, I think this is the rear flank of the tornado system. So I'll turn off my region manipulator, and I'll go to my appearance tab. I think I'm going to mask out some of these values so we just see the cold pool. So I'll drag my opacity sliders down and get something like that. So now we have just the cold pool, and we can see the vortex of our tornado right here. Okay, so now that we have some kind of orientation, we kind of know where the tornado is, I'm going to go to New and create my flow renderer. Double click that. and this will take a minute. There we go. So on the variables tab for the flow renderer, you can tell, like the barb renderer, we can select either 3D or 2D variables. Lee's dataset has no 2D variables, so I'll stick with 3D. One thing I'll note is if you try to create a new renderer and your dataset does not contain a certain dimensionality of variables, then you're not going to be able to create, for example, 2D data or contours unless you have 2D variables, and vice versa for 3D. So I'll cancel out of here. The default variables, Vapor tries to default with U, V, and W variables for flow and barbs. Those are usually the fields that people are after. So my default variables are U interp, V interp, and W interp, which are interpolated values for my X, Y, and Z vectors of wind. Data fidelity, I have no control here because I imported my data. This is not VDC, so we are looking at full resolution data here. So my renderings will take a little bit longer, and I won't be able to turn the resolution down, but I think that'll be fine for demonstration purposes. This data set is big, but it's not so massive that I can't demonstrate with it. So the next thing, you'll notice we have, well, I guess I can go ahead and just turn it on, and we can get our first flow rendering. And it's going to be, I think, kind of busy. Yeah, it's hard to tell what's going on here. So we're going to make a few adjustments so we can tell what these streamlines are doing, where they're originating from, like where they start, where they end, and we'll try to put them in a location that makes more sense. It's more of an interesting location to see what the wind fields are doing. So the first thing we'll see in our seeding tab is our integration settings. The first thing is the flow type. We are currently doing streamlines. We'll do another video on path lines later. The direction. With streamlines, you can integrate your paths or your streams forward, backward, or bidirectional. We're just going to stick with forward for now. The integration steps are how many increments we are advecting the streamlines along. The vector field multiplier is it usually should be set to 1. If your domain is if the extents of your domain are defined in meters and your wind field is defined in meters per second, then 1 is what you want. Your domain is congruent with the units of your wind field. But if for some reason your domain is in kilometers and your wind field is in meters per second, you can multiply your wind field by 1,000 using this tool, and then your wind field will be in units of kilometers per second, which is congruent with the units of your domain. But we are dealing with meters per second and meters, so we are good there. There's also controls for periodicity. You can make any axis periodic, so if a flow line advects outside of your domain, let's go to our home viewpoint, and okay, right here on the horizontal, this is our x-axis, and if we enable x periodicity, if a particle advects through the I guess the extents of your x-axis, it will reemerge on the other side, kind of like in a Pac-Man kind of style. So your domain is can be made periodic if you need it to be. So those are the integration settings. Next are the distribution settings, and this is defining how your seeds, we call a particle that we throw into the domain a seed. So flow is advecting seeds in Vapor. So our seed distribution settings are defining how we are placing seeds within the scene. And right now we're placing a grid in the scene, a 5 by 5 by 5 grid. If I change my z-axis seeds to 1, right now we are just distributing our seeds on a 5 by 5 grid on x and y, and just 1 smack in the middle of our z-axis. There's some other options here that I'll get into, but I think I want to make a meaningful rendering with our defaults in the gridded seed distribution first. So I'm going to move on to the rake region. So the seeds are distributed by a box that we call the rake. If I go to my navigation tab and go to region, we usually see this box and it's controlling the geometry, the region that we're rendering to. But if I'm in my flow renderer on the seeding tab, these control the rake, which is the box that we are throwing our seeds into. We can control the rake by right-clicking on this box and dragging So now I have, as we'll see once the rendering is calculated, we'll have a 5 by 5 grid of seeds on X and Y, all placed in the middle of the Z-axis like what we had before. I guess the rendering did complete. So this is different from the geometry editor because the seeds can travel outside of the rake. The rake is only defining where we're placing the seeds. So I'm going to go ahead and constrain my rake along the vortex, the main vortex of the tornado. And now we can see how our streamlines are advecting with this placement. Let's see if I can narrow this in a little bit more. And another thing I think I'd like to do is bring the rake down at the base of the tornado. So now we can see where these trajectories are going according to the wind field with the rake region. And you can see my rake region is updating as I manipulate this box. You can alternatively, if you know discrete values of a region you're interested in, you can type them in here, or you can use the sliders. In my personal experience, I tend to use the box manipulator within the scene just to eyeball things and get a sense of how things are going that way. The last controller in the seeding tab is this option. We can target a file to write our flow lines into. So if we want to export the position of these flow lines into an external file, I can select a file that I'll write. Let's call it flow.txt, and I'll write that file. And then let's take a look at what that file looks like. I'll bring up my console and vi on flow.txt. And here we have a list of seed trajectories. Our seed ID number, each flow line or trajectory has an ID number, and so ID number 0 has an X, Y, and Z position, a time, and a value. So this is a user-defined time within the netcdf file. So X, Y, Z, time, and the value of the color variable at that point. So if we go to our variables tab, we can see that we're color mapping our flow lines according to our potential temperature perturbation. So that potential temperature perturbation value is being recorded in our file right here for post-analysis, or if you want to import these into another application, you can do that. So that's our seeding tab. The appearance tab is just like any other renderer. This is our histogram for potential temperature perturbation. We can apply opacity and make the flow lines transparent. We should be able to, at least. That might be a bug I need to report, but I can do that after this video. These should be turning transparent. Let's see, if we change the color, yeah, you can see the color does take effect, but the opacity is a no-op at this point. So we'll fix that before our release, hopefully by the end of this month, January 2019. Geometry, just like any other renderer, you can control the extents to which you are rendering at. So now that I'm in the geometry tab, my box editor is going to control just where I'm rendering, not the rake. So you can see I've cut off the top right there, and my Z maximum has gone down. I can bring it down through the slider, or alternatively through the box editor. And then our annotation renderer, same as usual, turn on your color bar. Whoa. Or alternatively, turn it off. So back to our seeding tab. The other kinds of seed distribution settings I wanted to talk about for our streamlines. Our other options are a random distribution biased towards a user-selected variable, or a user-provided list of seeds, which is given through a text file. If I click on random, you can see our grid distribution on X, Y, and Z will go away, and we're just given a discrete value, 50. You can go all the way up to 480, or all the way down to 1. The fewer streamlines that you're advecting, the faster your computation will be. Next I'll go to random with bias. And let's see, let's do 10 seeds with bias. And I think these streamlines are kind of hard to see. So I'm going to go to my appearance tab and I'm going to I'm going to double click on this color control point. It's going to delete it. And so now all my streamlines are just red. Back to my seeding tab. Um, back here with my random distribution with bias, we have 10 seeds with 0 bias weight. We're not taking our bias variable into account with a value of 0. I'm going to pick no, W, wait, should I do Z vorticity? I'll do W, the vertical wind field for now. And I'm going to go back to my geometry tab and extend this back up so we can see the entire rendering. So I've picked winterp as my bias variable with no bias. We can negatively bias so that we are preferring to place our seeds towards regions with low values of W, or we can positively bias it to target high values of W. So I'll go ahead and max out my bias for winterp, but it's kind of hard to tell, if this is really hitting regions where W is that high. So what I can do to demonstrate where the high regions of W are is I'll make a volume rendering, and then we'll make a volume rendering that only shows very high values of W. So my volume rendering is now targeting winterp. I'll go to my appearance tab, and I'm going to drag everything down. Everything is going to be masked and transparent except for this last little sliver over here. These are going to be the highest values of W. And let's turn that on and see if our seeds, they should be where the volume rendering is. I can tell right now it's going to be hard because the high values of my volume rendering are going to be, oh, let's see, is that, I barely have much of a volume rendering at all. I can see a couple of volumes right here. Maybe I'm masking out too much. So let's see if I can extend. There we go. And you can see the volume rendering kind of dynamically renders itself while you're making adjustments. That's just for interactivity. Once I release it, it should be back to its full resolution. Huh. Well, gosh, we seem to be stuck in interactive mode. So I guess I have a couple of bugs to report before our release. Let me see if I can maybe demonstrate this with the slice renderer. So I'll go to my slice renderer, and I'll go to my region, and I will bring it up. Oh, let's see if we can use the geometry editor. There we go. Okay, we'll go to our appearance, and I'm going to change my variable to winterp and do the same thing. I will emphasize, I will mask everything except for our very high values of W. Huh, maybe I'm masking too much. That's interesting. Huh, looks like our opacity came back after I did that. Alright, back to slice. Yeah, we're not seeing much of anything. I wonder, let's bring these over. Okay, there it is. So I guess the transfer function is reporting that there are values here, too small. Let's see, let's change our scaling to Boolean. Let's see if there's, no? Huh, that's interesting. Well, I guess the workaround for now is to bring our transfer function over to show more values of W. And you can see the high values are being shown, most of the low values are being dismissed, but we can see right here that the high values are the origin for where our flow lines, our streamlines, are being distributed according to the bias variable of W. So that was a choppy introduction to the flow renderer, but again, this is a development version of Vapor. We are actively fixing bugs right now, so this kind of thing we're making. I'll make a point that we at least talk about this. Whether or not we address this fix before release, I suspect we will. But yeah, those are the basics of our Streamline renderer. Next, I'll be showing how to use path lines, which again, these streamlines are time invariant. This is just one time step. If I go to my next time step, we can see that there is, well, there's not, these are going to be drastically different. The streamlines will change their position. There will be no relation between the streamlines that occur at time step 0 and time step 1. Whereas path lines, there will be kind of a time-dependent advection happening. So you'll be able to see the particles flying around the actual scene. So we'll cover that next.